So welcome. This is the third of the lectures, video lectures on Lewis dots and chemical bonding that we're going to be looking at. And now we're going to take up cases where the molecules are a little more complicated. One of the compounds you can make when you combine sulfur and oxygen is sulfur dioxide. And in this case, it contains one sulfur and two oxygen atoms, which makes it a question: who's going to end up in the middle? Are the two oxygens going to be side by side with the sulfur out on one end? Or is the sulfur going to be in the middle surrounded by both the oxygens? And this is something that comes up anytime you're talking about a molecule. Who ends up in the center? Who ends up surrounding it? And there are basically two considerations for who ends up in the center. The first is simple and straightforward. Who wants the most bonds? If you have an atom that routinely likes to form 2, 3, or 4 bonds, it is much more likely to end up in the center than one that only wants to form 1 or 2 bonds. Well, how can you tell how many bonds an element wants to form? Well, that's simple. You simply take the number of valence electrons that atom has and subtract it from 8. So for phosphorus starts with 5 valence electrons. 8 minus 5 is 3, so phosphorus would want 3 bonds. Bromine, on the other hand, has 7 valence electrons. 8 minus 7 equals 1 bond. So the bromine wants to form 1 bond, the phosphorus wants to form 3. And so we see in the molecule phosphorus tribromide that the phosphorus is in the middle, surrounded by bromines. For the carbon dioxide, carbon starts out with 4 valence electrons. 8 minus 4 is 4 bonds. Oxygen, on the other hand, starts with 6 valence electrons. 8 minus 6 is 2 bonds. And so again, it is the carbon that ends up in the middle, since it wants 4 bonds while the oxygens only want 2 bonds, and so the one that wants the most bonds again ends up in the middle. That's not going to help us in this case, since sulfur also has 6 valence electrons. 8 minus 6 is 2 bonds. So both the oxygens and the sulfur want to form 2 bonds. So that's not telling us who's in the middle. So we have to consider something else. And the other thing to consider is who is the least electronegative element. Electronegativity is defined as a measure of how strongly an atom pulls the electrons in a covalent bond to itself. Basically, it's a description of how electron-greedy an element is. The more electronegative an element is, the more greedy for electrons it is. The general trend in electronegativity is fairly simple. First, fluorine is absolutely the most electronegative of all the elements. It'll pull electrons away from virtually anything else on the periodic table. After that, basically the closer you are to fluorine, the more electronegative you are. And so after fluorine, there is oxygen, chlorine, and neon, which are all next to fluorine. Of those three, we can ignore the neon. The neon's a noble gas. The noble gases do not have electronegativity since they don't generally form covalent bonds. So it's between oxygen and chlorine. Between those two, it is better to be in the same row than in the same column, and so it is the oxygen, which is next after fluorine, and the chlorine is the third most electronegative element. We have 3 elements that are 2 away from fluorine. They are nitrogen, sulfur, and bromine. Again, the nitrogen ends up 4th since it's in the same row as fluorine. Between the sulfur and the bromine's in the same column with fluorine. And so the bromine ends up 5th, the sulfur is 6th. And they are the 6 most electronegative elements. Here we see a chart of the electronegativity of all the elements in the main part of the periodic table. And like we said, fluorine in the upper right-hand corner, its electronegativity is 4. The other elements go down from there. Oxygen, chlorine, nitrogen, bromine, and sulfur bring us down to 2.5. All the rest of the elements have electronegativities less than 2.5. As we can see, almost all the metals have electronegativities between 1 and 2, and by the time we get to the alkali metals and the alkaline earths, they actually drop a little bit under 1. So to form our sulfur dioxide, we bring together our 2 oxygens and the sulfur. The sulfur gets to be in the middle. The sulfur puts in 1 electron, the oxygen puts in 1 electron, and we get a covalent bond. Then the other oxygen puts in an electron, the sulfur puts in an electron, and we get another covalent bond. And so we have a structure with the sulfur in the middle bonded to the 2 oxygens. But we have a big problem here. The big problem is that while sulfur, with 4 electrons to itself and 2 bonds, has its 8, both of the oxygens only have 7 electrons around them. And that's going to be no good. The more electronegative elements are the bullies in the chemical world. They like to pick on the less electronegative elements. That's why the sulfur ends up in the middle. And as a consequence, they're going to get happy first. A structure where the oxygens aren't happy and the sulfur is happy is simply not going to work. We could get around this if we bend the 2 oxygens close together and have the oxygens bond one to the other. That gives us this little triangle. There's all sorts of things wrong with that little triangle. The first and most important thing is the oxygens don't want to be bonded to other oxygens. It is always to the advantage of a more electronegative element to be bonded to something less electronegative. And so the oxygens don't want to be bonded together if there is anybody else to pick on. And they have somebody else to pick on. They have the sulfur. And so the oxygens will pick on the sulfur. To help us understand what's going on in the bonding of sulfur dioxide, we're going to use something that is known as has and needs. Has and needs is simple and straightforward. You take the number of valence electrons that all the atoms bring to the molecule, and then you figure out how many bonds you need. The sulfur is in the middle, surrounded by the oxygens. The sulfur brings 6 electrons, would like to end up with 8. The oxygens each bring 6 electrons and would like to end up with 8. But there's 2 of them. And so, altogether, we have 18 electrons, 6 from the sulfur, 12 from the oxygens. Now they all want 8. So to make everybody happy by just shoveling in electrons, we would need 24 electrons. But we don't have 24 electrons, we only have 18 electrons. We are 6 electrons short. And so we're going to have to make up for that number of electrons somehow. And the way we're going to make up that number of electrons is we're going to form covalent bonds. Every time an atom forms a covalent bond, it puts in 1 electron and gets a share of 2. So its number of electrons apparently goes up by 1 every time it forms a covalent bond. There's an atom at each end of that bond, and so the apparent number of electrons goes up by 2 every time we form a covalent bond. So if we are 6 electrons short, 24 minus 18, divide that by 2, we find out we're going to need 3 covalent bonds to make the molecule work. So the sulfur's in the middle, surrounded by the oxygen. 1 bond to each oxygen is not enough. That's only 2 bonds. We need a 3rd bond. And so we're going to have to put in a bond between the sulfur and one of the other oxygens. Now we have 3 bonds. That should be enough bonding. Now we need to fill in the electrons. The oxygen with a double bond already has 4 electrons, so it just needs 4 more, so we assign it 2 lone pairs. The oxygen on the other side has only 1 bonding pair, and so it needs 6 electrons to itself, so we assign it 3 lone pairs of electrons. The sulfur in the middle with a double bond and a single bond is 6, only needs 2 electrons to get to its noble gas count. So we have hung the molecule together. We have gotten 8 electrons around everybody. The last step in the Lewis dot structure is you have to count up the electrons. So starting on the left, the oxygen has 6 electrons to itself in its 3 lone pairs. It's sharing 1 pair with the sulfur, that's 8. The sulfur has a lone pair of itself. That brings us to 10. The sulfur is sharing a double bond with the oxygen on the right. That's 4 more, is 14. And the oxygen has 2 pairs, lone pairs to itself, which is 4 more, which is our 18 electrons. So everybody has a noble gas count, and we have the right number of electrons showing. And so is that our molecular structure? Well, yes and no. At this point, we're going to have to start talking about resonance structures. But that's for the next lecture. See you then.